Hello everyone, welcome to another video on artificial intelligence. In the previous video of this series, we have discussed about the various structures of agent program, and in this video we are going to discuss about problem solving agents, which is a type of goal-based agent. Without taking much time, let's get started. Our today's session is all about problem solving. First we will see what is problem solving. In that we will see what is problem solving agent is. After which we will discuss the steps performed by problem solving agent, which is goal formulation and problem formulation in detail. And then we will discuss the steps involved in problem formulation with root finding example. And finally we will move on to discuss some example problems in which we will see some toy problems and real world problems. Problem solving starts with identifying the issue. Problem solving is process of identifying a problem and developing possible solution paths and then taking the appropriate course of action. So problem solving is a technique to find a solution to achieve a goal. The term problem solving has different meaning depending upon the discipline. In computer science and in part of artificial intelligence, it deals with algorithms and techniques of algorithms, heuristics, and root cause analysis. The amount of resources required to solve a problem is described by computational complexity theory. In general, the problem solving process includes the problem determination, deduplication, analysis, diagnosis, repair, and so on. Problem solving agent in artificial intelligence is goal-based agent that focus on goals. It is one embodiment of group of algorithms and a technique to solve the well-defined problems in an area of artificial intelligence. And these agents are different from reflex agent who just have to map state into action and can't map when storing and learning are bigger. And these are the different stages that problem solving agents perform to get a desired solution. In first stage, it will clearly articulate and express the desired goal and the problem it's tried upon. In stage 2, it will explore and examine. Next, it will find the solution from various algorithms. Finally, it will step into execution. Probably you would know more of these jargons of AI once you are well through into the domain. Problem solving agents or intelligent agents are supposed to maximize its performance measure. Achieving this can be simplified if an agent can adapt a goal and aim to satisfy it. Problem-solving agents in AI mostly use these search strategies or algorithms to solve a specific problem and provide the best result. And these agents are goal-based agents and use atomic representation. The problem-solving agent performs precisely by defining problems and several solutions. So we can say that problem-solving is a part of artificial intelligence that encompasses a number of techniques such as a tree, B-tree, heuristic algorithms to solve a problem. The problem-solving techniques help in improving the performance of programs. AI-based searching algorithms provides high precision and maximum accuracy to results. These algorithms are faster than others in execution and offers multiple searching methods depending upon the problem faced. The goal-based agents that use more advanced factored or structured representation are usually called planning agents. The goal-based agent is capable of thinking beyond the present moment to decide the best action to take in order to achieve its goal. It uses a specific method known as search and planning, meaning that it targets the goal ahead and finds the right action in order to reach it. Google's Waymo driverless car are a good example of goal-based agent, as they are programmed with an end destination or goal in mind. The car will then think and make right decision in order to deliver the passenger where they are intended to go. One of the requirements for creating robust real-world AI application is to build a system capable of deciding which action should be performed to perceive a goal. Goal formulation is a technique for creating goals for an agent to achieve. Problem formulation is a step in problem definition that is used to understand and decide a course of action that need to be considered to achieve a goal. Every problem should be properly formulated in artificial intelligence. Problem formulation is very important before applying any search algorithms. Now let's see what is goal formulation and problem formulation in detail. Goal formulation is a technique for an agent to determine which goals needs to be achieved. Goal formulation is the process of setting goals that help an agent to organize its behavior by limiting the objectives. This goal formulation is based on current situation and agent's performance measure. And this is the first step in problem solving. It organizes the steps and sequences required to formulate one goal out of multiple goals as well as actions to achieve that goal. We can consider the agent's goal to be a set of states. The agent's task is to find out actions in the present and in the future that could reach the goal state from the present state. The major challenge in goal formulation or developing representation for an agent to reason and recognize when new goals need to be formulated due to plan failures. From the figure, the goal formulation make use of case library to formulate a goal state. To achieve this goal state, the system computes the action required to reach the goal state from the current state and then builds a plan. That is the input to the system or current world state and the case library. The task of goal formulation component is to determine new goal state for the agent to pursue. The world state and the goal state are then passed to the planner, which determines the action necessary to reach the goal state from the current world state. The output of the system is a plan for the agent to execute. We can define goal formulation as given here. Given the world state and the agent current state, formulate the agent's new goal state after executing the actions in the world. So we can say goal is a set of desirable world state in which the objectives have been achieved. The current and initial situation or starting point for the goal formulation. The action cause transition between the world states. The problem formulation is process of deciding what actions and states to consider for a given goal. In this technique, the problem is precisely defined. The definition should comprise a precise specification of initial and final situation with acceptable solution to the problem. And in this process, the major step is to select the best problem solving technique and then applying it to the particular problem. In general, an agent with several immediate options of unknown value can decide what to do by first examining the future actions that eventually lead to the states of known value. So in problem formulation, we decide how to manipulate the important aspects and ignore the others. So without doing goal formulation, if we do the problem formulation, we would not know what to include in our problem or what to leave or what should be achieved. So problem formulation must follow the goal formulation. Sometimes there may be a cycle of iterations between goal formulation and problem solving until one gets an efficient solution. After goal formulation and problem formulation, the agent has to look for the sequence of action that reaches the goal, and this process is called search. A search algorithm takes the problem as an input and returns a sequence of action as output. After the search phase, the agent has to carry out the actions that are recommended by the search algorithm, and this final phase is called execution phase. So the agent has to formulate, search, and execute. Searching is the most commonly used technique of problem solving in artificial intelligence. We refer the searching technique as a finding information. So the process of looking for the sequence of action that reaches the goal is called search. Once a solution is found, the actions it recommends can be carried out, and this is called execution phase. And thus the searching algorithm helps us to reach for a solution of a particular problem. Okay, then before we get into more about problem formulating phase, we need to first understand what is problem in terms of problem solving agents. Problems are the issues which come across any system, and solutions are needed to solve that particular problem. A well-defined problem has 5 components: a start or initial state, a description of actions available to an agent, a description of what each action does, also called a transition model, a goal test, and path cast. The first component that describes the problem is the initial state, that is the agent starts in. The problem can be analyzed into more specific components. First of all, it consists of 2 situations, a present one which we call as the initial state and the desired one which we call as a goal state. The agent task is to get from initial state to goal state by means of series of actions that change the state. The problem is solved if such a series of action has been found or goal has been reached. In general, problem solving is a component of goal-directed action or control. For example, if a taxi agent needs to get to location B, but the taxi is currently at location A, then the initial state of the problem would be location A. The second component that describes the problem is a description of possible actions available to the agent. For a given state S, actions returns a set of actions that can be executed in S. We can say that each of these actions is applicable in S. The third component is the description of what each action does, which is called the transition model. It is specified by a function result of S, A that returns the state that results from doing an action A in state S. Together, the initial state, actions, and transition model define a state space. The state space forms a graph in which the nodes are states and the link between the nodes are actions. A path in state space is a sequence of states connected by a sequence of actions. The goal test determines whether a given state is a goal state or not. Sometimes there is an explicit set of possible goal states and the test simply checks whether the given state is one of them. The last component of the problem is the path cost, which is a function that assigns a numeric cost to each path. The problem-solving agent chooses a cost function that reflects its own performance measure. The solution to the problem is an action sequence that leads from initial state to goal state, and the solution quality is measured by the path cost function. And an optimal solution has the lowest path cost among all solutions. The step cost of taking an action A in state S to reach the state S dash is denoted by C of S, A, S dash. Now let's see an example of simple problem-solving agent, which is a goal-based agent. It decides what to do by finding sequence of actions that lead to desirable states. As I mentioned earlier, an intelligent agents are supposed to maximize their performance measure, and achieving this is sometimes simplified if an agent can adapt a goal and aim at satisfying it. To illustrate the agent's behavior, let us take an example where our agent is in city of Arad, which is in Romania. The agent has to adapt a goal of getting to Bucharest. Now suppose the agent has a non-refundable ticket to fly out of Bucharest. In that case, it makes sense for the agent to adapt a goal of getting to Bucharest. Courses of action that don't reach Bucharest on time can be rejected without further considerations, and the agent decision problem is greatly simplified here. Goals helps in organizing the behavior by limiting the objectives that the agent is trying to achieve, and hence the actions it needs to consider. So setting a goal or goal formulation is the first step in problem solving, and it is based on the current situation and the agent's performance measure. Here the agent's task is to find out how to act now and in the future so that it reaches a goal. Before it can do this, it needs to decide what sort of actions and states it should consider. If it were to consider actions like moving left or turning right, the agent would probably never find its way to Bucharest. Because at that level of detail, there is too much uncertainty in the world and there would be too many steps in a solution. And now the agent have to decide what action should be taken to achieve the formulated goal. And this process of deciding what actions and states to consider for a given goal is called problem formulation. For now, let us assume that agent will consider actions at level of driving from one major town to another. Each state therefore corresponds to being in a particular town. Our agent has now adopted the goal of driving to Bucharest from Arad. 3 roads lead out of Arad, one towards Sibiu, one to Timisoara, and one to Zerend. None of these achieves the goal unless the agent is familiar with the geography of Romania. In other words, the agent will not know which of its possible action is best, because it does not know enough about the state that results from taking an action. If the agent has no additional information, that is, if the environment is unknown, then it has no choice but to try one of the actions at random. But suppose the agent has the map of Romania, the point of map is to provide the agent with information about the states. So the agent might get itself into action it can take. So the agent can use this information to consider subsequent stages of hypothetical journey via each of 3 towns, trying to find a journey that eventually gets to Bucharest. Therefore, once it has found a path on map from Arad to Bucharest, it can achieve its goal. In general, an agent with several immediate options of unknown value can decide what to do by first examining the future actions that eventually lead to the state of known value. To be more specific about what we mean by examining future actions, we have to be more specific about the properties of environment. Now we assume that the environment is observable, so the agent always knows the current state. That is, if the agent is driving in Romania, then each city on the map has a sign indicating its presence to the arriving driver. So in this environment, the initial state is known and the agent sensor detects all aspects that are relevant to the choice of action. We also assume the environment is discrete, so at any given state, finite number of actions can be performed within it. And this is true for navigating in Romania because each city is connected to a small number of other cities. We will assume the environment is known so that the agent knows which states are reached by each action. So an agent having an accurate map suffices to meet this condition for navigation problem. Finally, we assume that the environment is deterministic, so each action has exactly one outcome. Sometimes the agent might accidentally reach Zerend instead of Sibiu. In that case, it must have a contingency plan to drive from Arad to Sibiu and then to Râmnicu Vâlcea. Fortunately, if the agent knows the initial state and the environment is known and deterministic, it knows exactly where it will be after the first action and what it will perceive. Since only one percept is possible after the first action, so the solution can specify only one possible second action and so on. And that process of looking for the sequence of action that reaches the goal is called search. A search algorithm takes a problem as input and returns a solution in form of action sequence. Once a solution is found, the action it recommends can be carried out, and this is called the execution phase. While agent is executing the solution sequence, it ignores its percepts when choosing an action because it knows in advance what they will be. So an agent that carries out its plan with closed eye must be quite certain of what is going on. And we call this as an open loop system because ignoring the percept breaks the loop between agent and environment. And here is a simple problem solving agent. It first formulates a goal and a problem and searches for the sequence of action that would solve the problem and then executes the action one at a time. When this is complete, it formulates another goal and starts over. And this is a pseudocode for simple problem solving agent. And you can see the agent takes its input as a current percept and returns an action. And this agent maintains a sequence of actions and initially it is empty and it maintains the state which describes the current world state and it maintains a goal which is initially null and it maintains a problem which is the problem formulation. When we look at the body of the pseudocode, we have three basic steps. First, we need to formulate a problem and we need to search a solution for a problem and we need to execute the solution. And these two lines of code will formulate the goal and formulate the problem. After formulating a goal and problem to solve, the agent calls a search procedure to solve it. It then uses a solution to guide its action, doing whatever the solution recommends as the next thing to do, typically the first action of the sequence, and then removing that step from the sequence. Once the solution has been executed, the agent will formulate a new code. The goal formulation is process of setting a new goal, and problem formulation is process of deciding what action and states to consider for a given goal. After the process of problem formulation, the next step is search. The process of looking for a sequence of action that reaches the goal is called search. And the search algorithm will take the problem as an input and returns the solution in form of action sequence. And here you can see the searching algorithm is taking the problem as input and the problem is the output from the problem formulation. So during the problem formulation, we create a problem and that is provided as an input to the search algorithm. And the search algorithm will return a solution for the problem as a sequence of action. And now we need to execute those actions that has been specified in the sequence of actions and which is called as an execution phase. And these two lines of code is an execution part. That is, once the solution is found, the action it recommends can be carried out and this is called as an execution phase. To understand these steps, let us take an example of finding a route for a given map. And we will try to understand what are the different steps in the pseudocode will do. And now we have the percept as the input. And let's say the sensor that we have our GPS sensor. And also whatever the input that is specified by the passenger from the keypad as his destination. That is, whatever destination is specified would be the part of the percept. So let's say the current percept is Arad. That is, we are in Arad. And that is the location that GPS says that we are in Arad now. And the input's destination is Bucharest. So these two values constitute the current percept. Using the current percept, we will update our state. So we will use the previous state and the current percept. Using that, we will update our state. That is, we will create a new state. The new state would be, currently we are in Arad and our destination is Bucharest. Next, we will use a state that has been created to formulate a goal. Since the passenger has entered his destination as Bucharest, in this step we will formulate a goal. That is, we will decide our goal. That is, we need to be in Bucharest. And next step is problem formulation. As I mentioned earlier, to formulate a problem, you need to specify the current state or initial state, the actions, the transition models, goal test, and path cast. And here we are not discussing all the 5 components and we are taking only the initial state and the goal. Now we will formulate a problem. Our initial state is in Arad and goal is to get to Bucharest. And this is our problem. For this we need to search and find the solution. And we will ask the search algorithm to find the solution for this problem. And the search algorithm will take the problem as input And the problem is our initial state is in Arad and the goal is to be in Bucharest. And that is provided as an input to the search algorithm. And the search algorithm will provide a solution for this problem. And the solutions are the sequence of actions. On executing the sequence of action, we will result in achieving the goal. So on executing these actions, we will reach our goal. And that's what we do in our execute phase. And this is a solution provided by the search algorithm for our problem. Now we need to execute this sequence of actions. So for that, we will take the first item from the sequence. There are 3 items in the sequence. We will take the first action, which will be go to CBU. See, in the next line, we are going to take the rest of the sequence, which means we're gonna discard the first and to take whatever the rest. And we will assign it to sequence. And the sequence will be assigned a new value. There is go CBU will be deleted. Go Fagaras and go Bucharest will remain in the list. So that's what we will have after this line. And now this action will be returned, that is the action will be performed by the actuators. Once this action is executed, we will again call this function problem solving agent with new percept, but this time the sequence will not be empty like before. Since we have 2 items, so we will not go inside the if condition. Instead, we will come directly to the action where we take the first item from the sequence. So what is the first item now in the sequence is go Fagaras. Now we will take the next item from the sequence for the next action. And then we take the rest of the sequence, which means the first item is left and the rest will be go to Bucharest. And that will be our new sequence. That is, after executing this line in pseudocode, this is what we will end up with. And the new action, which is go Fagaras, will be returned as the action to be performed. And when we perform this action, we will reach Bucharest. After the action is complete, again this function is called. As we execute this function one more time, we check whether the sequence is empty or not. And it is still not empty because we have one more item in the list. So again we will not get into the if part. Instead we will come to this line of code. And this will take the first value, which is go Bucharest. And that's the action number 3 that we will perform. And next we will take the rest from the sequence. If we discard the first item, there will be nothing else in the list. So now the sequence will become empty list. Now we return the action, which is go Bucharest. And this will take the first value, which is go Bucharest. And that's the action number 3 that we will perform. And next we will take the rest from the sequence. If we discard the first item, there will be nothing else in the list. So now the sequence will become empty list. Now we return the action, which is go Bucharest. And this will be performed by the agent. Once the action is performed, again we will call this function with a new percept. And this time the sequence will be empty. As you can see, the sequence is empty list. Now we try to formulate a new goal based on whatever the new input is provided. So based on the input from the new passenger, we will formulate a new goal and formulate a problem. And then we will search for a solution of a new problem. And this is how the agent will work. This part of code is not entered during the execution state. So once we found the solution for the problem, we will not enter the if condition because our sequence list will not be empty. And also you may notice when we are in execution state, we don't actually make use of the percept. Because our actions are determined, so the percept is not used. We will make use of new percept only when our previous problem is complete and sequence list is empty. Then our new percept will again be used to formulate a new problem and we will search the solution for the problem. The important part in the pseudocode is search algorithm, and there are different search algorithms. And in next video, we will talk about different search algorithms. While explaining the pseudocode, we have seen only 2 components of the problem, which is the initial state and goal state. Now let us see all the 5 components of the problem. A problem can be defined formally by 5 components, which are initial state, actions, transition model, goal test, and pathcast. The initial state is the agent starts in. For example, the initial state for our agent in Romania might be described as in Arad. So the initial state is the starting point of problem. Action is formulated using a successor function that describes the possible action. So a successor function returns the possible actions available to the agent. So for a given particular state S, actions returns the set of actions that can be executed in S. So we can say that each of these actions is applicable in S. For example, from the state in Arad, the applicable actions are go CBU, go Timisoara, and go Zerend. To be simple, actions are action set used to move from one state to another. And next is transition model, which is a description of what each action does. and it is specified by a function result of s comma a. And this function returns the state that results from doing an action A in state S. And here we use the term successor to refer any state reachable from the given state by a single action. For example, we have result of in arad, goes errand equals in errand. So the transition model defines how one can shift from one state to another. Together, the initial state, actions, and transition model implicitly define the state space of a problem. So states are total states in a problem. And the state space forms a directed network or a graph in which the nodes are states and the link between the nodes are actions. The map of Romania can be interpreted as a state space graph, and we can see the road for two driving actions, one in each direction. And a path in state space is a sequence of states connected by sequence of actions. The goal test, which determines whether a given state is a goal state. The goal state is also known as a goal or a solution state or a final state, which is the finishing point of a problem. Sometimes there is an explicit set of possible goal states, and the test simply checks whether the given state is one of them. And here the agent's goal in Romania is a singleton set that is in Bucharest. The path cost function that assigns a numeric cost to each path. The problem solving agent chooses a cost function that reflects its own performance measure. For the Romania problem, the path cost might be its length in kilometers. The step cost of taking an action A in state S to reach S dash is denoted by C of S comma A comma S dash. We will consider the cost of the path is the sum of the cost of each step. A solution to a problem is an action sequence that leads from initial state to goal state. And the solution quality is measured by the path cost function. And an optimal solution has the lowest path cost among all the solutions. So far, we proposed a formulation of a problem getting to Bucharest in terms of initial state, actions, transition model, goal test, and path cost. And this formulation seems reasonable, but still it is a model, which is an abstract mathematical description, and it is not a real thing. When we choose to travel from Arad to Bucharest, the state of the world includes so many things, like the traveling companions, the current radio program, the scenery out of the window, the proximity of law enforcement officers, and the distance to the next rest stop, the condition of the road, and the weather, and so on. All these considerations are left out of our state descriptions because they are irrelevant to the problem of finding a route to Bucharest. So the process of removing detail from a representation is called abstraction. Then what is the appropriate level of abstraction? Now consider a solution to the abstract problem. For example, the path from Arad to Sibiu to Râmnicu Vâlcea to Pitești to Bucharest. This abstract solution corresponds to a large number of more detailed paths. So we could drive with the radio on between the Sibiu and Râmnicu Vâlcea and then switch it off for the rest of the trip. If abstraction is valid, we can expand it into a solution in a more detailed world. If abstraction is useful, you can carry out the actions in the solution, which is easier than the original problem. So remove as much detail as possible while retaining the validity and usefulness. So the good abstraction involves removing the details as possible and ensuring that the abstract actions are easy to carry out. So if we are not able to construct useful abstractions, then an intelligent agent would be completely swamped by the real world. The problem-solving approach has been applied to a vast array of task environments. We list some of the best known here, distinguishing between toy and real-world problems. A toy problem is intended to illustrate or exercise various problem-solving methods. These toy problems are used by different researchers to compare the performance of algorithms. Whereas the real-world problems are much harder and we usually care about the solutions. And here's a list of problems that can be solved by AI, which includes traveling salesman problem, Tower of Hanoi problem, water jug problem, NQN problem, chess, Sudoku, crypt arithmetic problem, magic squares, logical puzzles, and so on. Now we will talk about both toy problems and real-world problems. And we will talk about the toy problems like vacuum world, 8 puzzle, 8 Q's problem, and real-world problems like route finding problem, airline travel problem, and VLSI layout. Let us take the example of vacuum world that was introduced in the starting of the series. There is a vacuum cleaner agent and it can move left or right, and its job is to suck up the dirt from the floor. And the problem for the vacuum world can be formulated as here. The state is determined by both the agent location and the dirt location. The agent will be in one of the two locations, so each of which might or might not contain dirt. Therefore, there are 2 into 2 power 2, which is 8 possible world states. And a larger environment would have n into 2 power n states. And initial state, any state can be designated as an initial state. Next, actions. In this environment, there are 3 actions: move left, move right, suck up the dirt. Larger environment might also include up and down. Next is transition model. This is a function which defines change from one state to another. The action have their expected effects, except when the agent is in leftmost square, the action is left. When the agent is in rightmost square, the action is right. And the square is clean when the action is to suck. Next to the goal test, it will check whether all the squares are clean. And path cost, each step costs 1. So the path cost is the number of steps in the path. So the goal is to clean up all the dirt. That is, the goal is equivalent to the set of states 7, 8. And the vacuum world problem is a toy problem and involves only discrete locations and discrete dirt. Therefore, this problem is a toy problem, and there are many real world problems like automated taxi world. And we will try to formulate the problems of real world and see what would be the states and actions in upcoming series. And this is the state space diagram for the vacuum world problem. There are 4 different types of problems, which are single state problem, multi-state problem, contingency problem, and exploration problem. In single state problem, we will have a complete knowledge about the world state and also the complete action knowledge. Here the agent always knows its world state. In multi-state problem, we don't have sufficient knowledge about the world state and actions. Here the agent only knows which group of world state it is in. In contingency problem, it is impossible to define a complete sequence of action that constitute a solution in advance because the information about the intermediary states is unknown. In exploration problem, the state space and effects of action is unknown. Now we need to clean the world using a vacuum cleaner. And the world has just 2 locations. In this case, there are 8 possible world states. And there are 3 possible actions like left, right, and suck. The goal is to clean up all the dirt, that is, the goal is equivalent to the set of states 7 and 8. Suppose the agent sensor gives the information about which state it is in, that is, the world is completely accessible. And suppose it knows exactly what each of its action does, then it can calculate exactly what state it will be in after any sequence of action. For example, if the initial state is 5, then it can calculate the result of action as right and suck. This simplest case is called single state problem. Suppose the agent knows all of its effects of its action, but the world access is limited. Then the initial value will be one of the state from 1 to 8. That is, it knows the action right will cause it to be in one of the state 2, 4, 6, 8. In fact, it can discover the sequence right suck, left suck is guaranteed to reach a goal no matter what is the initial status. So when the world is not fully accessible, the agent must reason about the set of states that it might get to rather than the single states. This is called the multiple state problem. Suppose the suck action sometimes deposits dirt when there is none. Then if the agent is in state 4, sucking action will take place in one of the state 2 and 4. And still there is a sequence of actions that is guaranteed to reach the goal state. Suppose the agent is in one of the states 1 or 3. The agent might formulate the action sequence first suck and then move right and then suck. The first action would change the state to one of the state 5 or 7. And moving right would then change the state to 6 and 8. If the agent is in state 6, the plan will either succeed or fail. That is, we don't have any fixed action sequence that guarantees a solution to this problem. So the agent can solve the problem if it can perform sensing action during execution. For example, we are starting from one of the state 1 or 3. First it will suck the dirt and then move right. Then it will suck only if there is a dirt there. So in this case, the agent must calculate the whole tree of actions rather than a single sequence. That is, the plans now have a conditionals in them that are based on the results of sensing actions. and we call this as a contingency problem. Many problems in the real world are contingency problems. This is why most people keep their eyes open when they are walking and driving around. The single state problem and multi-state problem can be handled by similar search techniques, whereas contingency problem require more complex algorithms. The last type of problem is the exploration problem. In this type of problem, the agent has no information about the effects of its actions. So the agent might experiment and gradually discover what its action do and what sorts of states exist. This is a search in the real world rather than in a model. We also know the 8 puzzle problem by the name of n puzzle problem or sliding puzzle problem. The 8 puzzle consists of 8 numbered movable tile set in 3 into 3 frame. One cell of the frame is always empty. The puzzle can be solved by moving the tiles one by one in a single empty space, and then we can achieve the goal state. The state description specifies the location of 8 tiles in 9 squares. Here the blank space is in one of the 9 squares. Any state can be designated as the initial state. We define actions as movements of blank space, left, right, up or down. Next, transition model. For a given state and action, this returns the resulting state. The goal test will check whether the state matches the goal. Path cost is length of path. That is, each step cost 1. So the path cost is number of steps in path. The 8 puzzle problem belongs to the family of sliding block puzzles, which are often used as test problem for new search algorithms in AI. And this family is known to be NP-complete. The name NP-complete is short for non-deterministic polynomial time complete. In this name, non-deterministic refers to non-deterministic Turing machines, a way of mathematically formalizing the idea of brute force search algorithm. A NP-complete problem is a class of computational problems for which no efficient solution algorithm has been found, and many significant computer science problems belongs to this class. For example, the traveling salesman problem and the graph covering problems. And we will discuss this in the upcoming series. The 8 puzzle problem has 9 factorial by 2 possible states. 8 puzzle problem has a property that exactly half of all permutations can be reached from any starting state. There is 9 factorial is total number of possible configuration of the puzzle, whereas 9 factorial by 2 is the total number of solvable configurations. There is exactly half the configurations are impossible to reach from any chosen starting point. So we divide total configuration, that is 9 factorial by 2, to get the total number of states that can move step by step to the solution. If you draw a graph of every single state with every single possible transition out of that state, you will end up with 9 factorial by 2 states with 9 factorial transitions. There are states that exist but don't fall on the graph, and those are unsolvable ones. The 15 puzzle problem has around 1.3 trillion states, and the random instance can be solved optimally in few milliseconds by the best search algorithms. The 24 puzzle problem has around 10 power 25 states, and random instance takes several hours to solve optimally. Next is 8 queues problem. The goal of this problem is to place 8 queues on a chessboard such that no queues attack any other. The queue can attack other queues either diagonally or in same row and column. From the second figure, we can understand the problem as well as the correct solution. It is noticed from the figure that each queen is set in the chessboard in a position where no other queen is placed diagonally in a same row or column. Therefore, it is one right approach to the 8 queens problem. For this problem, there are two main kinds of formulation: the incremental formulation and the complete state formulation. In the incremental formulation, it starts from an empty state where the operator augments a queen at each step. That is, placing the queens one by one on the board. In the complete state formulation, it starts with all 8 queens on the chessboard and moves them around, and we save them from attacks. The steps involved in incremental formulations are given here. The state is arrangement of 0 to 8 queens on the chessboard. In initial state, no queens on the board. Action refers to adding a queen to any empty square. The transition model returns the board with a queen added to the specified square. The goal test will check whether the 8 queens are placed on the chessboard without any attack. There is no need for path cast because only final states are counted. So therefore we will have approximately 1.8 into 10 power 14 possible sequences. The complete state formulation is better than incremental formulation, and the steps involved in this formulations are listed here. Here the state refers to arrangement of all 8 queens, one per column, with no queen attacking other queen. Actions include moving the queen at the location where it is safe from the attacks. And in this formulation, it will reduce the state space from 1.8 into 10 power 14 to 2057, and it is easy to find the solutions. Now let's move on to real world problems. We have already seen how the route finding problem is defined in terms of specific locations and transitions along links between them. The route finding algorithms are used in a variety of applications. Some, such as websites and in-car systems that provide driving directions, are relatively straightforward extensions of Romania problem. Others, like routing video streams in computer networks, military operations planning, and airline travel planning systems, involve much more complex specifications. Now let's see the airline travel problems that is solved by travel planning websites. Each state includes a location and the current time. The initial state is specified by the user query. The action includes take any flight from the current location in any seat class, leaving after the current time, leaving enough time for within airport transfer if needed. The transition model includes the state resulting from taking a flight will have the flight's destination as the current location and the flight's arrival time as the current time. The goal test will check are we at the destination by some pre-specified time. The path cost depends on monetary cost, waiting time, flight time, customs and immigration procedure, seat quality, time of day, type of airplane, frequent flyer mileage awards, and so on. Turing problems are closely related to route finding problems but with an important difference. Now consider this example. In this example, the problem is to visit every city in the figure at least once, starting and ending in Bucharest. And here the action includes the trips between adjacent cities. And we have the state space, which is quite different. Each state must include not just the current location but also the set of cities the agent has visited. So the initial state would be in Bucharest, visited Bucharest. A typical intermediate state would be in Vaslui, visited Bucharest, Vlsi, Vaslui. The goal test would check whether the agent is in Bucharest and all 20 cities are visited. The traveling salesperson problem is a Turing problem in which each city must be visited exactly once. And the aim is to find the shortest tour. And this problem is said to be NP hard problem. It means you cannot guarantee to find the shortest path within a reasonable time limit. And next we are going to discuss about VLSI layout problem. The VLSI layout combines a huge number of circuits into a larger integrated circuit. VLSI is the process of creating an integrated circuit by combining thousands of transistors into a single chip. The VLSI problem is also known as general layout problem. It is the problem of embedding a graph into a grid of minimum area, which is NP-hard. The VLSI layout problem requires positioning millions of components and connections on a chip to minimize area, minimize circuit delays, minimize tray capacitances, and maximize manufacturing yield. This layout problem has a logical design phase which is usually split into two parts, that is cell layout and channel routing. In cell layout, the primitive components of the circuits are grouped into cells, each of which performs some recognized functions. Each cell has a fixed size and shape and requires a certain number of connections to each of the other cells. So the aim is to place the cells on the chip so that they do not overlap, so that there is a room for the connecting wires to be placed between the cells. Channel routing finds a specific route for each wire through the gaps between the cells. These search problems are extremely complex but definitely worth solving. With that note, we have come to the end of the session. In upcoming videos, we will present some algorithms capable of solving them. Please take up time to subscribe our channel and thank you so much for watching.